Hello viewers, welcome to Big Boy Physics, and in today's video I'll be discussing with you a problem from the topic of rotational motion. And this problem, if you when we'll be solving, you'll be realizing that it's a modified version of the Pathfinder problem from the rotation checker understanding. Well, later I'll tell you which number it is. But there was some problem in Pathfinder also, something like this. There were two cones and you had to find the steady angular velocity of the second cone when the first cone had been rotated by omega naught. The same question is actually asked but in a different manner. In this question, they are given a disk and a long cylinder. Then the same thing you have to apply, just you need to know bit of concept about it. Okay, so try this question for 2 to 3 minutes, then we'll be getting started. Okay, coming to question, a long cylinder of radius r naught which is rotated around the axis with an angular speed of omega naught has been pressed without applying friction to the axis against a disk of radius r rotating around its axis. The line of contact between the disk and the cylinder is along a disk of radius as shown in figure 61. So this is figure 61 and this corresponds to question. First question is you have to determine the steady or stationary angular velocity of the disk providing that there is dry friction between the cylinder and the disk. Okay. Now to do this kind of question you have to assume one thing, that normal is distributed evenly, that at any point the normal would be just uniform. Let me explain what it means, that if the normal as a function of x from the distance x is given as n as a function of x, then n as a function of l x dn by dl dx is actually constant. It means that is actually which means 0 means if you take any dx element, then the normal at it will be some constant c into x into dx. This means that pressure is uniformly distributed on the surface, hence normal is uniformly distributed, one thing you can assume. Okay, first question is actually the prerequisite of Pathfinder itself. Determine the stationary angular velocity. Now one thing you must know about friction is that, suppose you have a body of mass capital M and another body of mass small m. Suppose it moves with v1 and this capital M moves slower than v1 with some velocity, suppose v2. Then what will be the friction on m? The friction acting on m will be minus mu mg into v1 vector minus v2 vector by modulus of v1 vector minus v2 vector. So this quantity basically gives the unit vector along the relative velocity. This quantity gives the unit vector along the relative velocity. So yeah, we'll be using that theorem only. Now what will happen in this case is that, suppose the disk is rotating and the line of contact of the cylinder, long cylinder with the disk be this line OB. Okay. Now since I said to that normal to be distributed uniformly, so at a distance x you consider a strip of dx, then the normal dn on this strip will be some c times dx, because pressure is uniformly distributed. I told you to assume it earlier. Now see that when the disk will rotate with some steady angular velocity, what it's said to assume that omega mu, when it's rotating with omega mu, observe that the points near the center, the points near to the center will have almost velocity tending towards 0, and points away from the center will have velocity nearly tending to be very large, that is omega mu into r. Okay, these are far points and these are near points. So what will happen, that this cylinder will be slipping on the nearer points and cylinder will also be slipping on the farther points, but the velocity of the cylinder points will be larger near the near points with respect to the disk contact points, and in the farther side we can see that the long cylinder's velocity relative to the point of contact of the disc is actually larger, is smaller. Thus, in some region, the friction will be acting on the disc in this direction, and in the other region, the friction will be acting on this direction. Now, since we assume that normal to be uniformly distributed, thus friction is also uniformly distributed. So I can say that the dn is equals to c into dx into mu, and d tau, that is dn. Now d friction, what is the differential friction acting at this point, will be c into mu into dx. Now can you tell me the what is the differential torque due to this friction? The differential torque d tau will be x into df, which will come out to be c mu x dx. Now this friction in the right hand side region will provide you clockwise torque, and due to left hand side region will provide you anti-clockwise torque. Now if you consider the v cap as the relative velocity of the cylinder with respect to disk, then this integral from 0 to r should be coming out to be 0, because there will be a certain moment when v cap will tend to change its direction, right? Now I am assuming that till x is equals to x naught, this friction torque due to friction is clockwise, and from x naught to r this is anti-clockwise. So what I'll do is that c integral c mu into integral dx dx 0 to x naught is equals to c mu integral x naught to r x dx. From here you will get the equation x naught square is equals to r square minus x naught square, and you will get x naught is equals to r by root 2. So this is the point. This can be called as the stationary point, or the point which is moving with the same velocity with respect to the cylinder, long cylinder. Means this point will tend to remain at having no friction, and the region right of x is equals to x naught, that is x equals to r by root 2, will have friction acting on the upward direction, and the rest region, that is x greater than x naught, will have downward friction. So this will act kind of as a pivot point or the stationary point, and this point will have velocity same as the contact point of the longest cylinder. So I can say omega mu into r by root 2 is equals to omega naught r naught. Omega naught r naught is the relative velocity of the cylinder's contact point. Okay, this is the velocity of the cylinder's contact point will be equal to the velocity of disk's contact point at r x is equals to r by root 2. From here you will get mu omega mu is equals to omega naught r naught into root 2 by r. So that's the answer to first part. First part was relatively very simple. Coming to second part, determine stationary angular velocity omega mu of the disk rotation in case of lubricated friction, case, and find the ratio omega eta upon omega mu. They're also saying that they assume the force of lubrication to be exerted per unit length of contact is proportional to the relative velocity between the contacting surface. Okay. Now coming to second question. Second question is another. The same idea is actually applied in second question. Suppose you have this disk and consider a point x at a this point at a distance x, and consider the differential element dx. Okay. Now consider this cylinder, long cylinder. I am marking with red color. What is the velocity of the contact point of cylinder? Is equals to omega naught r naught. Velocity of point at that point of the disk can be written as omega eta into x. Omega eta into x. Now what is the relative velocity? Relative velocity will come out to be omega naught r naught minus omega eta x. Now you can assume this to be some length, suppose a, this width covered is a. Just for simplifying the calculation, we know that the friction is equals to eta a dv by dx. So I can say if the layer of the film to be t, then I can say that friction will be eta A will be A dx into what is dv, omega naught r naught minus omega eta x. This is the relative velocity, and dx is t. So observe that eta a and t are constant, and my point of interest is omega naught r naught minus omega eta x dx. Okay. Now in this case we are not required to find any such stationary point. We can directly get the result. Just what will be d tau? D tau. 1 minute. There's some problem. Yes. So the problem is solved. Now what will be differential torque? D tau will be eta a by t into omega naught r naught minus omega eta x into x dx. Now the summation of the torque or the integral of this torque from 0 to r should come out to be 0, right? Then only it will attain the steady angular velocity. Just cancel out eta a and t. You will get omega naught r naught into x dx. 0 to r is equals to omega eta x square dx. 0 to r. From here you will get omega naught r naught r square by 2 is equals to omega eta into r cube by third, and then you will get omega eta. Let me write it in red color. Yeah, omega eta is equals to 3 omega naught r naught by 2 r. Okay, and so that's the answer to the second part. Second part was relatively simple and easy to integrate as compared to first part, because in first part we were dealing with the unit vectors, and in second part we were dealing with the velocity vector. Integration of unit vector along with the unit vectors is relatively tougher as compared to integration with v vector. We know that integration of v vector dt will come out to be s vector, that is the displacement vector, but integral of v cap dt we need to use some integration. Okay, or else it will be difficult to find it. So yeah, that's the difference between the first part and second part. First part we dealt with v cap, that is why we need to find the rest point, or the point with respect to which the cylinder is at rest with respect to the disk. Okay, in first part that is why we required the stationary point concept, and in second part it was just do the blindly the integration and get the value. Okay, now they're asking k you can take it as a homework. You'll get 3 by 2 root 2, and if you further evaluate you'll get some answer. So take the say, part 2, find the ratio k omega eta by omega mu to be as a part of a homework, and comment me in the comment section the answer of k. What is k is equals to omega eta by omega mu, and the value. Try to use your hands to calculate rather using calculator. Okay, so thank you, have a nice day.